Hey physicists, what's the crack? So today what we're doing is we're going to figure out to describe the structure of optic fibers. So a lot of you have optic fibers in your houses, especially the new internet. So you might have heard like BT optic fiber. It makes like faster internet. Okay, so optic fibers. What they look like is you basically have a wire or a cable, and the inside part is called the core, and it's protected by the cladding. Okay, so it's going to label a diagram so I know to talk about it. There's my core, and there is my cladding. Okay, so you've got core in the middle and the cladding outside. Okay, so the first thing you want to talk about is that the cladding is there to protect the core. Okay, so just one mark already, just bullet point it. The cladding protects the core. Okay, the next thing is I know that when we're using optic fibers, we need light rays to go in, or EM waves to go in. When they go in, I want this signal to go the whole way across the wire. So what I need to happen is total internal reflection. Okay? So I want total internal reflection to happen so that this signal keeps traveling across the whole length of my fiber. Okay? So I don't lose any of that signal. So again, total internal reflection, and make sure I don't lose any of that signal, because then I'm going to get a worse quality image over here. And also for data protection, right? So sometimes we're transmitting information along here, and I don't want anyone else to discover what that information is because some of the signal got lost through the cable. Okay, so we have to remember what total internal reflection is. Okay, so the way I remember it is you do your key stage free diagrams first. So I have to figure out, is total internal reflection because it goes from more dense to less dense, or because it goes from less dense to more dense? So I would just draw a diagram. So let's say this is water and this is air. There's my normal at 90 degrees to my boundary from key stage 3. So if I have a light ray or an EM wave going from water into air, I know that light or EM waves travel faster in air. So when it travels faster, it bends away from the normal. Okay. So here is my angle of incidence, and between the normal and the ray, is my angle of refraction. So what I can see is if I keep increasing this angle of incidence, what's going to happen is this ray is going to keep bending towards the normal. And then there's going to be some angle called the critical angle, so critical angle, for which this ray then gets refracted along the normal. Okay? And that's my conditions for total internal reflection. If I want this ray to be reflected inside total internal reflection, I need to use an angle greater than the critical angle. So just to show that, if I use any angle that is greater than the critical angle, so this angle is going to be greater than the critical angle, the ray is no longer refracted out into the air. The ray is going to get totally internally reflected. And that's what I want. So just to confirm, in order to get total internal reflection, I need my ray to travel from somewhere that is more optically dense somewhere that is less optically dense. Okay? So that means my core must be the more optically dense, and the cladding must be less optically dense. So I'm going to write that because that's a property, a description of my optic fiber. So again, the core is more optically dense than the cladding. And I'm going to tell them why, so that total internal reflection can occur. Okay, last thing I want to think about then is sometimes what they do is want to figure out what type of EM waves we put in here. Okay, and one thing we want to do is we know that all EM waves, they travel at the same speed in air, but they travel at different speeds in water, in oil, in solids. So I need to make sure that the ray of light that I'm using, or the EM wave I'm using, is monochromatic. So what monochromatic means is mono stands for one, and then chromatic stands for color. So I want to use monochromatic light so that I only have one wavelength, one color of light going in here, so that the signal remains constant at the end. Because if I was to use light of different colors, of different wavelengths, they're going to travel at different speeds inside the core, so they're going to be reflected at different angles. So my signal won't be sharp at the end. My signal will be broadened. So what I'm going to say here is that I want to make sure to use monochromatic light. So again, to recap, we just want to make sure we use monochromatic light so that our signal is sharp and not that it's broadened. Okay, so that's our description of our optic fiber.